modern airport, the first thing you notice is the geometry. Launching a commercial jet requires thousands of acres of flat, cleared earth. We have reached a physical limit in our dense modern cities. Civil planners cannot simply bulldoze 50 blocks of infrastructure to lay down a 3-mile strip of asphalt. This spatial constraint applies at the opposite extreme. In rocky valleys and snow-capped Himalayan peaks, carving out a traditional runway is a geographical impossibility. This is why engineers approach aviation access by looking vertically rather than searching for more horizontal space. Moving upward entirely bypasses the rugged terrain below. Achieving true last-mile connectivity, reaching both the deepest urban centers and the most remote villages, requires leaving the two-dimensional runway model behind. Astronomers face a remarkably similar constraint when observing the universe. For centuries, our view of space was limited to a single, flat layer of data, visible optical light. Relying strictly on the shapes we can see with our eyes means we completely miss the violent, high-energy engines that actually drive the cosmos. Whether we are trying to route delivery drones through urban canyons or trace the evolution of a galaxy, understanding these complex systems requires mapping invisible layers of data. Managing a handful of helicopters is one thing, but when a swarm of delivery drones and air taxis enters our cities, the primary bottleneck shifts from physical landing pads to the highly complex airspace above them. High-volume traffic creates an immediate logistical nightmare. If multiple flight paths converge on a single pad at once, the system faces instant gridlock. To solve this, developers use predictive software layers like the AHD-TCO framework. A modern vertiport runs a persistent digital wireframe twin that absorbs real-time variables like sudden weather shifts and incoming traffic density. An AI engine then cycles through millions of chaotic scenarios in seconds, eventually locking into an organized grid of green routes that assign landing slots with microsecond precision. Because the precise routing and timing instructions are perfected in the digital realm first, the system mitigates risks and physical collisions before they ever occur in the real world. NASA applies this exact same methodology to deep space, layering invisible datasets over physical reality to reveal the underlying mechanics of galaxies. The Chandra X-ray Observatory is designed specifically for this purpose. Its mission is to map the invisible million-degree physical phenomena occurring throughout the universe. When astronomers observe the Cigar Galaxy, optical light shows the shape of its central disk, while layered X-ray data exposes towering superwinds of hot gas blowing thousands of light-years out into space. In Centaurus A, this layered X-ray mapping isolates a high-energy particle jet blasted out by a supermassive black hole, cutting directly across the galaxy's dark dust lanes. This data also captures the extreme gravitational shockwaves triggered during physical collisions, showing us exactly where a smaller galaxy punched straight through a larger stellar ring. Without layering this invisible, high-energy data over optical shapes, the true forces governing the life cycles of these galaxies would remain completely hidden from our view. This blend of predictive software and vertical infrastructure has moved from research into active development. Implementing these intelligent networks can reduce delivery times to remote locations by 50%, shifting time-sensitive logistics and emergency services directly into the sky. This upward migration acts as a critical relief valve for the heavy transport needs that our crowded ground infrastructure can no longer sustain. On a much larger scale, this advanced mapping of invisible data offers a predictive model for our own cosmic neighborhood. By analyzing the chaotic collisions of distant galaxies, astronomers have generated a direct preview of the Milky Way's distant future merger with our nearest neighbor, the Andromeda Galaxy. Whether we are bringing runway-free mobility to isolated regions or tracing the origins of the universe, the path forward is clear. Human progress relies on our ability to map, calculate, and ultimately master the invisible spaces above us.